Recorded is rolling. So it's Tuesday, May 10th. You guys know you have the exam, AP exam in this class in a couple of days. All right, so let's go over this again. So guys, a couple of days from now, on Thursday, what class period do you have to leave for lunch? Third period. So you're gonna go to your third period teacher, say, hey, I need to leave at 11 o'clock, right? Right, go to the cafeteria, you have a special lunch just for you.
They don't open
And
the
then-
doors, though.
Oh,
Yeah, they just make us sit outside and starve.
oh, oh, really?
Yeah.
Okay, new news, bring your own lunch.
Bring your own
Are
lunch.
you guys gonna bring your own lunch on Thursday?
Yeah.
That is good to know, yeah, so.
Yeah, for CSA, they were like, you guys can sit out there, just chilling, we're like.
Then 11:30, be over at the gym, because it's supposed to officially start at 12, but you know, it takes some time to process, you know, get a seat and make sure all your cell phones are turned in, the whole thing, right? Okay, so talk about final exams a little bit. No, you won't have a final exam in this class. You usually don't for your AP classes because the AP exam is sort of like a replacement for the for a final exam. But no, nothing about this class. I mean, you might have some other classes that are not AP, so you might want to know where final exams. I know we've been looking at this a few times, but it's coming up on us. Take a look again. All right, so remember Monday the 23rd. Regular final exam start, but the seniors will be out of here by that time. Here's the senior final exam schedule. So for seniors, your first final, just regular school final exam. What else we May 12th, right? So same as the AP Physics. So there you go. So that is coming up. If you were a senior, I think I had a couple seniors in here. Right? Good note. All right. So we're just going to do a more exam review. I've been doing some exam review with you guys yesterday. Right, so I've got 3 ideas for what we could do, and let's do a quick vote because we got real short class today. We got like these 20-minute classes. So what are we gonna do with these 20 minutes? Right, so I'll give you guys 3 options. One option is here, just list some numbers. Right, one option is we can do kind of what we did yesterday. I'll just go unit by unit and throw some problems out there and just have you guys solve them. Just problems I make up on the fly, right, just like yesterday. Option 2 is I got some old MCQs that we can do. Option 3 is I do have an FRQ printed out ready to go, so we can just go over that. We can just go over it as a class, right? So let's do a quick vote. How many guys want to do kind of what we did yesterday? Just keep doing more like that. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, how many guys want to look at old multiple choice questions? 1, 2, 3, 4, 5, 6. 6. Okay. Does anybody want me to pull that old FRQ and we just do it as class? Yeah. All right. So we'll do more what we did yesterday. Of course, I mean, if you guys want it opted for something else, you guys know to go to AP Classroom. There's like full practice exams up there. You can take. All right.
I have sunglasses there.
So, let's. Ooh, I know what to do.
Not bringing out big
I'm
sunglasses.
gonna pull a kind of a tricky one. Right, you guys see this right here? Right, I wrote this one up a few weeks ago, so I forget what the solution is, but hey, let's solve it right now. So questions I could ask about this. You could ask what's the acceleration of the system. You could ask how far is it falling after some time. You could ask how fast is it falling after some time. You could ask how fast it's falling after some distance. You could also ask what is the tension in the string, right? There's a bunch of questions, right? Probably some other questions too. So let's solve for acceleration because that's probably a good place to start. A lot of things stem from that. What is the acceleration of the system, like the downward acceleration of this 1 kilogram guy? I'll solve it off screen while you guys are solving it and see if you guys can beat me to the answer.
No.
Oh, it hurts. That was a huge fix. Do you give me My part is called Pi Square. Pi Square. It's a time fixture of that Pi Square. If you want them to follow through, oh, and you have to buy it too. So.
Should be like a multi, you should like a.
Using a time.
Acceleration.
Did you just? Yeah. It was just something that I got, I was in a 5 seconds.
But she did a great job.
Yeah.
Yeah, she
So
did.
everyone was like,
My name is John. She's not mine.
Interesting. How about?
All right, who's got the answer? Who's got the answer?
You like suck down some Diet Coke. Making more.
We double check my work before I flash this in front of the screen. I think this looks right. All right, last call before I start going to solution. Anybody got the answer yet? We got it? All right, so start going over step by step. It's still see if you can reach the answer. Now, acceleration of that system. Were you guys thinking Newton's second law of motion, net force on total mass? Right? Yeah. Now, what is the net force? I definitely see that this one hanging has a weight. Guys, what's the weight of this guy? About 10 newtons. Let's call it 10 newtons, right? Right. Is that the only force that's going to drive the motion of this? There's one other force that matters. And what is that one other force? Friction. Yeah. Okay. So we got the weight of this one, like a gravitational force. Right? Now there are other forces. There's a tension that's internal to the system, so you don't count that because it doesn't. Right. There's this big block has its own gravity force and a normal force that just balance each other out. Right. But look, there's a coefficient of friction. Now, which coefficient of friction would you use? What do you think? Yeah, let's go with the kinetic. Right. Now, the static could be applicable if you wanted to know, like, what's the you might be asked, like, what's the minimum weight of this block to start the system? It starts from rest. Right. Yeah, you definitely want to make sure that it broke friction first so that it could actually start. Right? And once it is in motion, then okay, once it is accelerated, go with kinetic, right? And isn't here, start to take a look at this. So we got net force on total mass, right? Acceleration is. Right? Got the weight of the hanging block, that's M1G, so it's the weight of hanging. Right? And subtract the friction force. Now, friction force, isn't that coefficient of friction times the normal force? Right, you guys get that? You guys probably have one of these going around. I picked these up because there was standardized tested here the other day, but I put them on the front desk so you guys can pass those back. Okay. And see, where is, here, it's this one, right. What's that inequality? I mean, not even. Oh, okay. So friction force says less than or equal to coefficient of friction times normal force. Right? Of course, the inequality part just applies to the static part. So here we go. All right, we got that. Okay. And then start popping in numbers. Right. So the weight of the hanging one, well, it's 1 kilogram times 10 meters per second squared. So there's your 10 newtons that you guys told me. Here's coefficient of friction, the kinetic friction. Okay. And then the normal force of the large block. Well, the large block has a mass of 8 kilograms, so would have a weight of 80 newtons. And because it's on horizontal surface, just think there's a normal force of also 80 newtons holding it up, right? Okay. And then how much mass total is being moved around? Well, 8 plus 1 kilograms, right? Run those numbers, you should get 2 newtons acting on 9 kilograms is about 0.2 meters per second squared. We can also call it 0.2 Newton per kilogram, right? You guys got that? So when you guys see something really similar to that in a couple days, you guys can do that because I bet there's going to be something pretty similar to that. I'm not pretty soon.
Yeah.
All right, how about that? Let's do harmonic motion. Harmonic motion. So see if you guys remember this from scratch. If you have a pendulum swinging back and forth, you guys remember the time period for a pendulum? Of course, it's on your equation bank also, but See if you guys remember this from scratch. What's the time period for that pendulum? You guys remember that? Very good. Right. So the longer the pendulum, the more time it takes to swing back and forth. And the more the gravity field, the less time it takes to swing back and forth. Right? How about this? What if I had this string was 4 times as long, 4 times as long? What would happen to the time period to swing back and forth? It would double. Because the square root of 4 is 2. Right? Well, factor 4 inside the square root, right? It'd be 2. Right? What if it was 9 times as long? Yeah, 3 times the time period, right? Like I said. Okay. What if you hot planets? What would let's say you have 4 times the gravity? What happens to the time period? Half. Right? How about this? You're an astronaut. You're jumping around different. So you go to some moon. You pull out lots of different pendulums on some moon. And you want to know, what's the gravity field? So you make a table of values. This could totally be an AP question. AP likes the kinds of questions we're about to draw up here. Okay? You have different lengths and different corresponding time periods. So check, 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 check. They'll give you some numbers, right? Okay. And then this astronaut wants to linearize the data so that the slope of all this data, so your data points could be bop, bop, bop. See if they're all like direct relationship in a line. Okay. Line best fit. Right? So the slope of this exactly represents the gravity field of the moon. What do you put on each axis? And there could be multiple correct answers. So I'll do some work off screen. You guys probably want to pull out the paper and try manipulating that formula. Okay. What can you put on the vertical and the horizontal axis to linearize this data so that the slope represents the gravity field? Well, I think this was a recent quiz question, wasn't it? Or I think it was. All right. You guys got an answer? Yeah, what's your answer?
I have L versus T over 2 pi squared.
Yeah, that'll work. That'll work. All right. So yes, one saying
Yes.
L versus T on 2 pi and that whole thing being squared. Okay. That would work. Let me switch ink color. Show you what I came up with. I came up with 2 pi quantity squared L versus T squared. Right? That would be another solution. Right? So the blue ink is one solution, the red ink is another solution. Let's go with. Let me show you how I got mine. Mine's like one step away from Warner. So start with this formula. Right now, what you're solving for, you want this to represent a slope, right? So think to the end. You want to get it in this form where it looks like y equals mx and represent the slope. I'm talking about like straight from an algebra textbook. That's what m represents in algebra, right? Like slope of the line, y equals mx. Right? Okay, so how can you make this look like that? Right? Well, rearrange it, and you want to get this g in the numerator. So you have to unbury it from the square root. So you have to square both sides. Maybe do a cross multiply. You guys remember cross multiplication? I cross multiply this there, cross multiply this here, right? So I get it in this form, right? Something equals g times something. Okay, so g is occupying the space that represents the slope, right? And those other 2 spaces are occupying each of the axes, right? Vertical axis, horizontal axis. Okay, so you guys can linear. You guys know you're gonna have to linearize something, probably for an FRQ, right? But good chance multiple choice too, right? You guys can do that. Okay. How about let's do this. Let's take this pendulum question. What if I give you a length of, make up some numbers here, call it 3.5 meters. Let's turn this into like a adventurous archaeologist problem, like from your textbook. Right, this guy's swinging on a vine that's 3.5 meters long. Let's say this angle starts at 30 degrees. And I want to know how fast is this guy going at the bottom? Let's say this guy's on Earth, right? So how fast is this guy moving down here? Close to V. Okay. All right, I got an answer. You guys got an answer? What'd you get? Yeah, I got one. Natalie got 3.07 about 3.06. All right. So through here. So got this pendulum swinging. I'm looking at this height change. I might call this H, right? Now, what is this H? You can figure out in terms of L and theta. Here it is in terms of variables, right? A little bit of geometry. You guys see a nice looking right triangle right here, where this side of the right triangle is the cosine component. Right. This whole thing is also L because L is the same thing. So L minus the cosine component of L is looks like this or this, same thing. Okay. Right. I can go over to conservation of energy. So I got all potential energy at this point, all kinetic energy at this point, if you define height zeros like that dash line. Okay. So boom, boom. Solve for V. V is the square root 2gh, just like it's been over and over and over in this class, right? As long as you start from rest, right? And then, yeah, and of course, H is this expression, right? L times 1 minus cosine theta. Pop in your variable, pop in some numbers, and yeah, there you go. About 3.06, 3.07, somewhere in there, meters per second. How about this? What if instead of starting from rest, what if you kicked off? So you're swinging on a vine and you give yourself a push, right? The final velocity, can you just add that to the initial velocity? Like what if you push off at like 5 meters per second? Can I say 5 plus 3 is 8? Or do I have to embed that in conservation of energy? Say 1/2 mv naught squared plus blah, blah, blah. Do that. Yeah, okay. I have to do it that way. If I just add it at the end, I'm gonna get something that's wrong. Right? So you have to do 1/2 mv naught squared plus this equals this and then solve it. It works out a little bit differently. Okay. Ooh, what about this? I'm gonna give this guy a mass. Let's say this guy swinging on the vine has a mass of 50 kilograms. Okay. Can anybody tell me what is the tension in this vine? Let's make it a 2-part question. What if he's just hanging at rest? If he's hanging at rest, what's the tension in the vine? 500 newtons. Now, if he's swinging, is it still gonna be 500 newtons? No. All right, so you guys solve it, I'll solve it. That number might be helpful. All right, go ahead. All right, what is the tension in that vine? who's got an answer? Who's got an answer? We start. Remember to save us a minute here. Okay. All right, so did you guys come up with that for the free body diagram? Okay. I'm just gonna flash the solution up here. You guys want to look at that? I will post this recording to Google Classroom.